In this video, we're going to get back to this idea of diagonalization and generalize it beyond where we introduced it for real symmetric matrices, now for more general matrices as well. So in addition to real symmetric matrices, which was the special case we've dealt with already, we're now going to look at symmetric matrices with repeated eigenvalues, as well as non-symmetric matrices, and see what's the same and what's different about this diagonalization process. Just a reminder, we're talking about similarity transformations here. So these are transformations that do not change the values of the eigenvalues. And so we say the two matrices are similar, and that's what we mean when we say that. So the new matrix D, just like before, is going to be a diagonal matrix. It's going to have the eigenvalues of A sitting along the diagonal, just like before. I think it's helpful to summarize the four possible cases with symmetric, non-symmetric, distinct eigenvalues, and non-distinct or repeated eigenvalues. So we've already looked at the case with symmetric A and distinct eigenvalues. In that case, the eigenvectors were mutually orthogonal. So the U's were really Q's, they were mutually orthogonal. We've touched on the possibility of a symmetric matrix with repeated eigenvalues. And remember, we said we could choose the constants such that the eigenvectors are mutually orthogonal, but in general, we can only say that they're linearly independent. I have not proven that, but it turns out to be the case. Similarly, for non-symmetric matrix A with distinct eigenvalues, we can also prove that the eigenvectors are linearly independent, not orthogonal in general, but linearly independent. The fourth possibility is if we have a non-symmetric A, repeated eigenvalues, and in that case, we cannot say very much about the eigenvectors. In fact, this diagonalization process is going to break down a little bit. We'll talk about that in the next video to see what happens there. It almost diagonalizes. In that case, we get what's called the Jordan canonical form, which is not fully diagonalized. So we're really going to focus on these three cases for now, and then we'll talk about this fourth case in the next video. The case where A is real and symmetric with distinct eigenvalues. We know that the eigenvectors are mutually orthogonal. They form a basis with respect to which we can do this diagonalization. We've already looked at that case. So now we're going to add in the possibility that our matrix is non-symmetric with distinct eigenvalues. So that's that third case in my little 2x2 summary table. And then we're also going to look at non-symmetric matrices with repeated eigenvalues, again, where you get this Jordan canonical form. We'll look at that in the next section. So far, the application of diagonalization we have in mind, and again, I did this for the purpose of having a geometric interpretation, was to look at quadratics. And there are a number of applications of quadratics, but we really want to spend time on this diagonalization process because there are even more essential applications for us, in particular in solving systems of linear ordinary differential equations. So this is something we do all the time as scientists and engineers, and so this will be a new tool in our toolbox to be able to solve them using this same diagonalization procedure that we're talking about now. In addition, SVD, or singular value decomposition, is also based on this diagonalization process. And then I've also mentioned a couple times the QR algorithm, which is a numerical algorithm that we use to get the eigenvalues and eigenvectors using a computer for large matrices. And that is also based on this idea of diagonalization, as we'll see. But in all of these cases, diagonalization can be viewed as a change of basis, a change of coordinate system. So we're changing the way we look at our quadratic. We're changing the way we look at our linear system of algebraic equations. We're changing the way we look at our particular problem in such a way that makes it easier to solve, easier to deal with. And so we're going to be using this tool, this diagonalization tool, for the rest of Chapter 2, and it's going to come up in other contexts as well throughout the book. Now, like this poor moose, you might be feeling a little, trepidatious. I've been talking about diagonalization quite a bit in the last number of videos. We're getting deeper and deeper into the details and into the weeds of this, but don't hide. Now's not the time to hide. So stick with me and we'll get through this together. So let's look at matrices with linearly independent eigenvectors. So that corresponds to 3 out of the 4 cases. Either of the symmetric cases and the non-symmetric case with distinct eigenvalues. This excludes the non-symmetric repeated eigenvalues case, but all the other 3 cases this includes, including the the real symmetric with distinct eigenvalues, for which we've already done, but we can also use this more general approach. So the eigenvectors are all linearly independent, and we're going to take advantage of that to do the diagonalization. So now the big difference that you're going to see is we're going to use the modal matrix U instead of Q. Remember, Q was an orthogonal matrix. It had orthogonal vectors as its columns. Now we're going to use the matrix U as the modal matrix, which has the eigenvectors as the columns, just like it did for Q. But now the only thing we can say about those eigenvectors is that they're linearly independent. They may or may not be orthogonal. And in that case, the similarity transformation, instead of Q transpose times A times Q, is now U inverse times A times U. Same A, and now it's the more general modal matrix U rather than Q. And we have to generalize the transpose to the inverse, and we'll talk more about that in a moment. The D matrix that we get is still diagonal, and it's still such that the eigenvalues are sitting on the diagonal. So that's no different than the special case that we've looked at before. So again, you're noticing the big change here is now we're using U instead of Q, so general modal matrix, and we have to use the inverse instead of the transpose because of that. So just to remind you, I'm reserving use of Q for orthogonal modal matrices. Okay, so U is a general modal matrix, and Q is a U that happens to also be orthogonal. So in order to prove that U inverse times A times U does indeed diagonalize A in the way that we just described, I'm going to show a little bit different proof than we did for the real symmetric case, but it ends up giving us the same result. So what I want to show is that D and A have the same characteristic equation. Now I know D comes from U inverse times A times U, so let's use that as the starting point. So the determinant of D minus lambda times I is equal to the determinant of U inverse times A times U minus lambda times I. Let's make this term look similar to the first term. I can multiply by U inverse times U because that's just the identity matrix, so it's like multiplying by 1, so that doesn't change the result. So let's write this as U inverse times I times U. So now you'll notice I'm pre-multiplying U inverse in both of these and post-multiplying U. So I can write this then, the determinant of U inverse times the quantity A minus lambda I times U. So now, if you remember from chapter 1, the determinant of the product of matrices is the product of the determinants of those matrices. So I can write this as, the order doesn't matter here because they're just scalars, the determinant of U times the determinant of A minus lambda I times the determinant of the inverse of U. Also from chapter 1, the determinant of the inverse of a matrix is just the reciprocal of the determinant of the matrix. So that's 1 over the determinant of U. So then these cancel, and I just end up with the determinant of A minus lambda I. So we've just proved that indeed the characteristic equation for D and the characteristic equation for A are the same, and therefore they are similar, and therefore this U inverse times A times U, which is equal to D, is indeed a similarity transformation. It does not change the eigenvalues of the original matrix. All right, so that's great. Okay, the next point I want to make is relating the Q and the U, and just getting back to that and make sure we're clear on that. So now we're using U inverse. If U happen to be made up of orthogonal and normalized eigenvectors of A, then that would mean it's orthogonal, in which case U inverse is equal to U transpose, and then we could write it as Q. So the Q transpose that we used for the real symmetric case is again just a special case of the U inverse under the circumstances that the eigenvectors are mutually orthogonal and normalized and not just linearly independent. They are linearly independent, but in addition they're also mutually orthogonal and normalized. So everything is consistent, and again, as I keep saying, the real symmetric case then, the Q transpose times A times Q, is just a special case of this more general diagonalization procedure. It is possible to prove this, that the n by n matrix A, it can be diagonalized in this way when there are n regular eigenvectors that are linearly independent. I'm not going to do that proof, but that proof does exist. So this is true for all symmetric matrices, whether distinct eigenvalues or repeated eigenvalues, and it's true for non-symmetric matrices as long as the eigenvalues are distinct. So again, this leaves that fourth case where non-symmetric repeated eigenvalues we need to treat separately. But the 3 out of the 4 cases, this holds. U inverse times A times U does the diagonalization. Just like we said in the context of real symmetric A, Q transpose times A times Q, this is even more important now. We don't actually have to evaluate the inverse of U times A times U because we know the result. The result is a diagonal matrix with the eigenvalues on the diagonal. So we actually don't even have to evaluate the U inverse and then do the matrix multiplication. We know the result. So in fact, there's really no advantage to the Q transpose times A times Q. Normally there would be because transposes are easier than inverses to evaluate, but because we don't have to evaluate the inverse, in this case there's no advantage there. Now we keep calling this the modal matrix. The Q and the U is the modal matrix. So in dynamical systems, we imagine that there are modes. So the modes come from the system itself, from the matrix representation of the system. It's based on the eigenvalues, the eigenvectors, and so that modal matrix encapsulates those modes. It encapsulates the information about those modes. And in fact, the general motion of a system then is just a superposition or a linear combination of those modes. And that's why we call it the modal matrix, even in context beyond that of dynamical systems.